Hi, everyone. So, yeah, we would like just to start with a very brief presentation of us. So, I'm Anna, an R&D information retrieval machine learning engineer in SIS. So, I mostly work in the integration of machine learning with search engines. Then I leave the word to Ilaria and Edward that will continue the presentation.
Okay, it's working. Yeah. Good morning, everyone. My name is Ilaria. I'm Italian and have been working at SIS since 2020. And yes, I'm a search consultant, and I mainly deal with the integration of machine learning with search engine and information retrieval system. Give to Edward.
Thank you, Ilaria. So I'm Edward Lambe. I'm the head of the data engineering team within the monetary and economic department of the Bank for International Settlements, which is quite a long title.
Okay, now just a bit introduction about our company, SIS, which means Search Services. It was founded in 2016. The headquarters is in London, but we are all distributed worldwide, especially in Europe. We are open source enthusiasts, and we are expert in Apache Solr and Lucene, Elasticsearch, and OpenSearch. We are active researchers, and we actively contribute back to the community. And our latest hot trends are large language model application, like the one that we show you today, neural search, natural language processing, learning to rank, document similarity, search quality evaluation, and relevance tuning. Now, up to Edward for the
So I'll
presentation.
just give a brief introduction to some of the work that we've been doing at the BIS with Anna and Ilaria and SIS. Just maybe by context, I think if I was to ask for a show of hands, probably very few would know who the Bank for International Settlements are. But that's a little bit by design. We try to fly a little bit under the radar if we can. But we're the oldest international financial institution in the world, and we were established in 1930. And we're based in Basel. And our mission is to support central banks in their pursuit of monetary and financial stability through international cooperation, and also to act as a bank for central banks. So we have a banking division, and they provide banking services for countries to manage their reserves. But the more important part of that mission statement is the international cooperation. And every 2 months, the central bank governors from our member banks come to Basel for 3 days to discuss topics that are of interest. And the monetary and economic department, where I work, the economists and researchers there provide the analysis and the research and the working papers that help guide those discussions when those central bank governors are here, or there in Basel. And a key part of that is the statistics that we as an institution collect from other central banks and national statistical institutes, but also collate and publish ourselves. And, you know, if we think of the keynote speech this morning, really I think what we're all striving for is evidence-based and informed policy making within national governments, but also having an informed discussion at an international level helps very much in keeping the stability of the financial system. In 2023, we modernized our data dissemination solution. So we launched what we call the BIS Data Portal. There, we're publishing 1.2 million time series in the public domain. That's a fraction of what we have internally. We have about 50 million plus time series internally to support the research of the organization. And we also implemented a Solr-based search on the time series themselves, and that's a weighted search across a number of the facets that you see outlined here. The data portal itself, it was designed with 4 key personas in mind. So the general public, journalists, academic researchers, and central bankers. And as you go through those personas, there's a graduated level of knowledge that we think those users will have. So for the general public user, we're looking at giving them statistical kind of introductions to the topics. But what we've done for the journalist and maybe the more kind of student academic researcher is our subject matter experts have provided a lot of tabular content and dashboards which really tell the key message of the data, because some of the data that we publish is quite complicated. And having our subject matter experts relay that information clearly through those tables and dashboards is a real plus. And then for the more advanced users, they can search for the individual time series they're interested in, they can download the content, they can bring that content within their own institution and do the research they want on their own analytics platforms. The data portal is built on SDMX. Again, I would imagine within this audience here, this is not a commonly known standard, but it's a standard for statistical data and metadata exchange, and it's been sponsored by the 8 international organizations that you see here. BIS itself are quite active in this domain. We're quite active in trying to promote the use of open source technologies in this space. We've published 2, I think, really important aspects or applications. The first being the Fusion Metadata Registry, which is the reference SDMX registry implementation that's now used by a number of international institutions and central banks, and equally PySDMX, which is a Python library to provide very easy access to the SDMX content that's being published within central banks and national statistical institutes. If this is of interest to any of you, I would invite you to visit the sdmx.io website. There's a lot of training material there, but also links to a lot of the open source tooling that's been made available in this space. So as I said, the BIS data portal, it's built with SDMX at its core, and there are a number of SDMX artifacts that we use to define the information model of the data, essentially, that we publish. And we use category schemes, which are essentially a kind of high-level aggregation or grouping of the statistical topics. We have data flows, which are the BIS published collections. Then we have the dataset definitions. This is essentially the table or the schema or the structure that we're publishing. The statistical concepts, which either describe or identify the time series in question. And then we have code lists, which enumerate all the different possibilities that are there for each concept. And this is essentially, as you see it displayed here, a hierarchy of the kind of information flow. And this can be used in the work that Anna and Ilaria will present to filter the time series information that we have, pass that as input context to the LLM for the LLM to make decisions as to what time series the individual may be interested in. So maybe just to talk quickly around the use case that we have identified. Which slide am I on? Sorry. This is a quick visual of the BIS data portal. This shows you some of the concepts that we have there. So the query that was entered was, what are the office space prices in Rabat? You can see here we have the topics. So this is the commercial property prices. So luckily we're in the right domain. You can see in the yellow, these are reference areas, or country encodings, essentially, giving us the geographical areas that may be of interest to the query. And then we have the dimensions being highlighted here as well. And these are identifying the time series. And the question is, can we use the LLM to actually select the appropriate filters to apply on the data collections that we have, so that users can quickly navigate to the time series that are of interest to them? So the engagement with SEAS, it's really been around how do we leverage the SDMX REST API and the LLM to assist that search process. We wanted to implement a more natural language search within the portal itself, and also try to provide search results where the existing lexical search engine was struggling. A key part of this is we want to make it clear to end users that they are using an AI-assisted search. And in doing that, we also want to provide the rationale as to why selections are being made. So that's a key aspect that we want to be able to display to people. And ultimately, we want to be able to share this with other institutions, other central banks, other statistical agencies, that they can deploy within their domain relatively quickly. And I think we've achieved that. And with that, I will hand over to Ilaria, who will take you through more detailed phases of the project.
Thank you, Edward. Okay, let's continue with the LLM-based search for SDMX data. Here, I just want to show you the API structure. So for this project, actually, we developed the process using the component that you can see in this diagram. So we have the AI Filter Assistant API, that is the main component that handles the search request from the user interface. So it receives an input, the user query in natural language, and then it delegated to the appropriate endpoint that we will see in a bit. We develop it using Python and FastAPI. And then in the initialization phase, we have the SDMX component, because a series of SDMX endpoints are triggered in order to retrieve all the necessary data and metadata that we need for our application. And then to improve the performance and also to avoid downloading every time the same data, we store locally all the data in a cache file. And then we have the OpenAI component, because one of the client's requirements was to use the OpenAI models, so there was no need to add an abstraction layer for the model inference, but we directly use the OpenAI natives API. Here, I want to show you at high level the process flow. So we have mainly 4 phases, let's say. We start with the data retrieval part. So at startup application, as already said, a series of SDMX endpoints are triggered in order to retrieve all the data, and we parse and organize it into efficient data structure like dictionary, and then we cache the data. And then we have the topic selection phase. So we ask the model to select, to extract the most relevant topic based on the user query. In fact, the input context in this phase is the list of all the available topics together with a short description. And with as a result, we will have the topics selected by the large language model related to the query plus the rationale. Then we have the country selection. So in this case, the input context is the reference area code list filtered by topic. And as a result, we will obtain the reference area selected by the large language model plus the rationale again. And finally, we have the dimension selection phase. In this case, we gave an input to the large language model, the data available per data flow filtered by country. And then as a result, we will get the filters selected, as Edward showed you before, related to the query plus rationale. Now I just want to show you a bit in details the various phases. So starting from the data retrieval, at the beginning we build this dictionary that we need both to give to the input to the large language model, but also to build the final JSON response of our application. The first dictionary is this one, topic to description dictionary. So you can see this is a dictionary where each key is a topic, and then the values are a short description related to the topic. Here, for example, we have commercial property prices, residential prices, and so on. And we use this dictionary, we pass this dictionary to the LLM for the topic selection. Then we have the country-related dimensions dictionary. So in this case, as you can see, we have each key is a data flow code, and for each data flow, we have a list of dimension related to the country. So, for example, we have the data flow 1 as just the reference area dimension, data flow 2 as 2 dimension associated, reference area rep city, and so on with all the other 27 data flow that there are in the SDMX. Then we have another dictionary, data flows 2 dimension. So in this case, is a dictionary per data flow again. And then for each data flow, we have a dictionary containing all the dimension associated to that data flow. And the values of the key in this case are their human readable description. So for example, for the data flow 1, we have frec dimension, which means frequency, ref area, which means reference area, covered area, and so on with all the dimension related to each data flow. And then we have another dictionary for each data flow, dimension to values. So again, for each data flow, we build a series of dictionary where for each dimension we will have all the possible value for each dimension associated with each human readable description. So in this case, for the frequency, we have A, which means annual, B, which means daily, business week, and so on. Why we build this kind of dictionary? Because if we give to the large language model something that is human readable, it will be readable also by the model, because it will be easier for the model to understand which dimension and values to select. Then I'll show you the endpoint. So we have mainly two endpoints. The first one is the topic selection endpoint. In input, it takes the user query, natural language. In this case, we have this example, cost per square meter for family houses in Austria. And the output of our endpoint is a JSON that will contain the topics selected by the large language model, in this case, residential property prices. That was the most relevant topic in this case for this query, plus the reasoning part. Now, we remove the reasoning just because we want to make the slides more readable and less dense with content, but I will read you the reasoning. So it was, let's think step by step in order to produce the selected topics. We need to identify which topics from the provided list are most important to the input text, cost per square meter for family houses in Austria. The input text is clearly related to the real estate, so residential property prices is the most relevant topic. So the model was able to understand that this was the most relevant topic. It is a list, so the model can return up to 3 topics. Here, I just want to show you a bit the prompt that we use for the topic selection. So we use the chat completion create endpoint from OpenAI, and in the role system there are the instructions. So in this case, the prompt is you are an expert in financial statistical data. You will receive a user query and a dictionary. The keys of the dictionary represent a topic or category. The values of the dictionary are the related topic description. You are required to select the most relevant topic for the given query. If you are unsure among a few topics, select at most 2 or 3 of them. And in the role user, we pass the input to process. So in our case, the natural language query plus the dictionary that I showed you before, so the topic to description dictionary. And here, the one important thing to show is the response format parameters, where you can pass a JSON schema in order to enforce a structured output for the model. So you will tell how the output should be presented, and Anna will show you better this part. And then I will show you the second endpoint, is the country dimension selected endpoint, because before I show you 2 different phases, but we have just one endpoint that takes in input the user query and the data flow ID. So in this case, this endpoint is at data flow level. So once one or more topics has been identified with the previous endpoint, with the previous call, we filter the data accordingly to the topic. In this case, a topic can be associated with 1 or more data flow. So we call this endpoint multiple times, one per data flow. And in this case, the pipeline is composed of 2 different large language model calls. One for the country, to select the country, and one to select the dimension. But in the output, you can see that in the JSON, we have both the responses. So the selected country plus the country reasoning, and the selected dimension plus the dimension reasoning. But we divide it into steps to give to the model, to filter the data by topic first and then by country, to give to the model less data, more relevant, in order to receive, to give to him less noise and to reduce, to get results that are more accurate. So even in this case, I removed the reasoning part, but I will read. So the country reasoning was the query explicitly mentioned Austria, which directly matches the geographical area Austria in the provided list. And for the dimension reasoning, the user query specify cost per square meter and family houses, which directly corresponds to the price unit of per square meter and real estate type of single family houses. No other dimensions such as frequency, covered area, real estate vintage, compiling agency, or seasonal adjustment are explicitly mentioned in the query, so they are not selected. So as you can see in the JSON response, we have all the dimensions associated with the data flow, but the model selects just two of these dimensions with the related values, and the other was left empty because the model didn't find explicitly mentioned in the query about this dimension. What are the limitations and lessons learned in this phase? So prompting structure are not always strictly followed by the model. So as of today, prompt engineering is far from ideal. So it's still about trying to interact with an entity that is not programmable at all. So you can, we have no visibility of what happened behind the scenes when the prompt is processed. So you can do empirical analysis tests, but you are not sure how the rules that you put in the prompt will influence the output. And also the more relevant context, so shorter and higher quality, the better the models perform. That is what I said before. So we decided to filter every time the data, so split the pipeline in different phases in order to give to the model less data, but with higher quality specific to that task. And then once you receive the dimension from the selected dimension from the LLM, how should the Solr query be executed? There are two options. You can apply the filter using the OR operator. This is useful if you have zero result query. So in this case, you will broaden the result set, potentially affecting the ordering of the result. Or on the other hand, if you have too many results, you can combine the filter using the AND operator in order to refine the results and making the filter more restrictive. Passing to Anna for the structure output.
Thank you. Okay, so now I would like to go in depth into the process of how we actually put together the taxonomy, the dictionary Ilaria shown us about the SDMX data, together with the natural language query of the user, to obtain the JSON output we have seen before. So, what we exploit was the structured output feature of OpenAI. Actually, it's just not only OpenAI feature, since it is also implementing some other large language model, both commercial and open source. But since we use the OpenAI model, we actually exploit this feature that allows us to be sure that we will obtain, as a response from the model, a specific JSON format. And the way we could define the format to obtain is through the JSON schema, declarative language. So we could actually specify to the model the list of key value we would like to obtain as answer. And the nice thing is also that we can define the data types of each of these values, so string, numbers, arrays, etc. And we could also add some additional constraints if we need. For example, we can specify the format, the pattern the string should have, or the minimum, maximum value an integer could assume for arrays, number of items, etc. So this actually was the main thing that changed our design of our pipeline, since it allows us to not have hallucination produced by the large language model. So how OpenAI obtained this kind of behavior from the model? So they proceed with two steps. The first one is the training of their latest GPT-4o model. And the idea is is to train the model to understand the JSON schema provided in input, and then to produce the best output possible that reflect that JSON. But the large language model is not deterministic, so we couldn't actually be 100% sure that the answer will be that kind of JSON format. So they needed to add an additional layer on this design. So an engineering approach, which is called constraint sampling or constraint decoding, where the idea is to actually translate this JSON schema into a set of grammar rules and then dynamically apply them during the generation phase of the large language model. So the large language model could only choose the token to return based on this subset of selected token that are the ones that will ensure us to obtain the JSON format we would like. So it is only going to choose the available valid tokens to return. And this is the part that actually gives us 100 reliability on the output format we have. Here is an example of the JSON schema we have used for the identification of geographical area from the natural language query. So as you can see, there is this main object that is the JSON schema with a name that generically represents the content, in this case identified geographical area. Then we have the schema itself with the list of properties, which are the main keys we will have in our JSON output with their corresponding values. In this case, we need to be returned the geographical area list and the rationale, as mentioned by Edward. We would like also to show to the user why it decide to select those values. And by now, geographical areas and the rationale, so the properties, needs to be put inside the required option of this JSON schema, since it is not supported the fact that a field is optional. So it is always required, and as shown by Ilaria, we will always have all the dimension returned. The only thing we can do is like make the model do not return any selection for that dimension if it is not found in the natural language query of the user. And the same is the additional property is set to false. This is the main idea of that option again. So the other two nice things we have here is the fact that we could add a description to both our properties. So this helps the model better understanding which kind of output we would like to see inside that part of the JSON. And then the type, that for geographical area is an array, while for the rationale is a string. And specifically for the geographical area array, we define the items inside this array, which are strings taken from this enum parameter here, this list of geographical areas, which are the ones that are valid for this data flow selected. And the nice thing is that enum list, since here we could actually put the exact value that are valid for the SDMX data. So the model could not return a geographical area that is not present in this list, or change a bit slightly the name of the geographical area, etc. So we could use this exact value automatically into the flow to filter, for example, in Solr, the final result list, without having to manage this kind of thing in different ways. And we also need the null value in the list, since, as mentioned before, no optional field is allowed by now. So this allows the model to actually return null if no geographical areas were found in the user natural language query. So a lot of very beautiful, nice things, but the JSON schema still comes with some limitation. Some of them are documented. So, for example, the total string size, so the size of all the string in the JSON schema, like names, descriptions, enums, the enum size that we could pass to the large language model, that is a reduced set of values. And then, as mentioned before, the fact that no optional field could be, by now, be set into the JSON schema. They are all required, so we need to exploit this null value to be able to actually do not include some of them. And finally, the enum parameters is for one of our specific extraction, for the topic one. It would be actually nice to be able to associate in the num list also the description of each topic present in the array, but by now only single strings are allowed, so we couldn't add this additional information. Moving to the test framework, so we actually develop also a test framework to check the quality of the large language model results. We started by 23 data flows and 24 queries selected by these domain experts. So we could identify this set of queries we would like to use for testing. And for the manual evaluation, we actually made the large language model calls Ilaria shown before for the topic and dimension extraction. And the idea was to generate an Excel file with the answers of the large language model for each of these query data flow couples, and use it to show the results to some experts and then obtain from them a manual review of the results. So we put here the topic extracted, countries extracted, the dimension extracted with the reasoning, but also the input context, so the JSON schema dictionary and values to check, to be sure that what we have was the expected values from the large language model. So it helps us in the debugging and explainability purposes. We use this set of queries also to decide which kind of OpenAI model to use. So we started with GPT-4o Mini, since from documentation, blog posts, benchmarks, we have seen that this was the most promising one along all of them, and we started with it. But we then decided to compare it with GPT-4o, which actually gave us better rationale and results. So we decided to move to that GPT model. And finally, the 4.1 was released, so we decided again to compare them to see how the answers and filter selected changes. And we have seen good results with this model with also a cheaper cost. So here in this table, we just put some comparison about the input context window, which is greater with GPT 4.1. Again, for the output tokens, the cost, which is slightly less than the GPT-4o, and the average query time, where we actually execute the 24 queries for each model and average the overall query time we have in response from both, and we have seen that they have comparable results, so we go with the 4.1 model. And finally, the automatic evaluation. So here, the domain expert selects 7 data flows and 12 queries, and we develop a PyTest file in order to create one test for each query, data flow, topic, call, and dimension. So what is the query and what we expect to be the JSON returned. And we decide that the test returns a success only if all the dimensions are exactly returned as we would like to see. So we need that all the topics and all the dimensions are correct in order to return a success for that specific test. Since the model is not deterministic, we actually need to iterate this process on this test and execute them several times. Since sometimes the model achieved the results, so it was a success, sometimes not. And we do this to calculate actually the percentage of successes among all the iteration we have done on the test. And so we were able to compute the percentage of success in topic extraction, dimension extraction, the overall calls to the large language model, and then also for each specific test, which allows us to understand actually also for which query the model performs better and for which other query the model was not performing as expected. There are some improvement idea on this kind of evaluation process. So generate more queries that could be done both by passing documents, BISC document to the large language model and ask the model to create some additional query for those documents, or also like creating some variation of the user collected queries, some specific experts extracted query. and then ask the domain expert to actually review this set. So the effort required to the person will be much less than ask them to create the overall data set by scratch. Also, some additional metrics could be exploited. Instead of this 0-1 test among all the dimension and value, we could actually create a graduated scale of how many dimension was good and how many not for each large language model call. So just the very last slide, sorry, futures work. So yeah, we would like also to test the few-shot integration in our large language model prompt. So we have already developed a few examples to pass, but it was like a to-do thing we would like to integrate in the prompt and see how it performs. It is better in some critical scenario. And then potentially fine-tuning the model for our specific tasks. Actually, we have this specific statistical data, so it could be an improvement probably to have this kind of fine-tuning on the model. Expanded the task framework as mentioned before, and also expose these results to the real user or internally domain experts to actually gather user interaction feedbacks and see on real case how the model actually performs, if it's returning the expected filters or not. Okay, here is a QR code of a survey in collaboration with Apache Solr PMC. So if you would like to participate, it would be very nice. And it's like about the open source technology that are used today, which is the focus of your work and this kind of thing, to understand better where we could enhance currently Solr integration improvements in the topic. Thank you.
Yeah, thank you very much. Do we have questions from the audience, also online as possible? I'm coming over here.
Hello. On one of the slides you showed that doing all this LLM pre-processing adds multiple seconds on average to a search call. Is that acceptable? And if not, how do you plan to bring it down?
The time, you said the average time?
Yes.
Yeah. So you mean this one?
Exactly.
Okay. I mean, actually, maybe we ask to the client if it's acceptable or not. Actually, we try to reduce also the prompt or to do some
we are running things in parallel. So the first call will identify maybe a number of topics, and when we have a number of topics, then the calls can fire in parallel. The average time, it's about 4 to 5 seconds if it's a complicated query. In the context of the data portal, where people typically come and are kind of interested in getting the content back, for us that seems like an acceptable kind of timeline. I should say we are looking at implementing this. We hope to implement this at the end of September, just prior to the SDMX Global Conference. We will also be kind of including caching, aspects like that, so that we don't have to do repeat calls to the LLM where we've already made those calls previously. So we would expect the performance then to kind of stabilize around that kind of 3 to 4, 5 second kind of mark.
Yeah, and also, for the topic selection was better. For the country selection, there was as I showed you before, there are 2 large language model calls, and also 1 for each data flow. So we try to parallelize in order to increase the speed. But there are also some.
Okay, then we have another question from our online audience. Did you consider combining some of those LLM calls using more complex JSON outputs to make it faster, e.g. combining topic and dimension selection?
No, for the moment, no, but this is something that we can consider to do it. Yeah.
Quick answer. Good. Do we have one more question here? Okay. Yep. Yeah.
When you're creating the JSON, is it going like first the first field and the second field and after each other? Because if that's so, you're first like deciding which topic is needed, and then you give the reasoning. It might be more helpful to first like let the model think about it and reason about it first, and then select a topic. It's kind of other way. It's kind of just like justification. The topic is already set, and then a justification. At least as far as I understand it.
Yes. Can you repeat the question? So what is?
Like, did you try it otherwise, or is it working like this? I'm not really sure if it's working like this.
Yeah, the model start to think and to.
But like in the JSON, there's first like the topic selection.
In the JSON, there is a list from which the topic can select the value. So it is forced to select from this list. Yeah.
And then you have like a reasoning field. And the reasoning field is generated later. So the model already like has a topic selected, right?
Actually, we don't know exactly how to parse the JSON internally, the JSON schema.
All right, thank you very much. If you have further questions, please come afterwards to the speakers and give them a round of applause. Thank you very much.